In this demonstration, we're going to show how optimization algorithms can be used to tune the frequency response of a hydraulic servo valve model. Here is our situation. We have a manufacturer's datasheet for a hydraulic servo valve. In the datasheet, we can see frequency response characteristics for the valve tested at 40% current and 100% current. You can see curves for the amplitude ratio and for the phase lag. What we need to do is to tune parameter values in our valve model until the frequency response generated by the simulation matches the characteristics shown in the datasheet. To do this, we'll use SimHydraulics and the optimization toolbox. The data shown in this datasheet was taken from a hydraulic circuit configured like this, where the input is the input to the valve control device, and the output is the flow rate in the external loop. The amplitude ratio is dominated by the power stage, which is modeled by these two blocks. The phase lag is dominated by the control device. Since the time constants in the power stage are much shorter than that from the control device, the phase lag measured here will be the same as the phase measured here. So for our tests, to tune the frequency response to make sure that it matches the phase lag, we'll simply measure our output at this point. We'll bring in the data from the datasheet and test it against the frequency response with our initial parameter settings. We can see that they're far away. We'll then use optimization algorithms to tune the parameters in our model until the frequency response generated by the simulation matches the data from the datasheet. I'll now switch over to the model so that you can see how this is done. Here is the model that we're working with. You can see the SimHydraulics model of the valve actuator device here. You can see that we've parameterized this model with 3 MATLAB variables. These are the parameters that we'll tune with the optimization algorithms. The first thing that we'll need to do is to generate a frequency response with the initial values of the parameters. We're generating a frequency response at 100% signal and at 40% signal. In this plot that we've just generated, you can see the comparison for each level of input signal with the data from the datasheet. You can see that in both cases we're very far from the characteristic. So what we need to do is set up an optimization to tune the parameters in the model until the frequency response generated by the simulation matches that from the datasheet. Let's see how we've set up that optimization. In this MATLAB script, you can see that we're using the optimization algorithm fmin_con. fmin_con is in the optimization toolbox and can be used to optimize parameters. fmin_con allows you to set up constraints on the parameter values. So we're going to do that. Here you can see we've defined a lower bound and an upper bound for the 3 parameter values that we showed you before. Let's see how we've defined the objective function. The objective function is what fmin_con is going to minimize. In this objective function, this is what fmin_con is going to execute each time. You can see that we're generating the test frequencies. So we're going to test the actuator at 100% signal at 2 different frequencies and then at 40% signal at 2 additional frequencies. These are the 4 points that we're going to compare in the objective function. Using FR estimate, we'll generate or calculate the phase at those 4 different points. And then down below you can see the custom objective function that we've created, where we are comparing those to we're comparing the frequencies measured in the frequency response in the simulation with the values from the data sheet. And by summing that all together, that generates the value f. fmin_con will attempt to minimize this value during the optimization. Now that we've seen how the optimization has been set up, let's run the optimization. By double-clicking on this block, we'll start the script that will run the optimization. In the MATLAB command window, you'll see updates from the optimization as it is running. And you can see that we have the value of the objective function here. So you can see that as the optimization runs, this value will shrink as fmin_con manages to reduce the value of f, or bring the frequency response closer to the values from the datasheet. Every time that the simulation up here blinks and you see a new plot on the scope, that means a new simulation has been run with new values of the parameters. And you can see it's alternating between 100% signal, the 2 points, and then the 40% signal, the 2 points, or the 2 frequencies. You can see that even after this short period of time, the objective function has been shrunk significantly. It started at around 36,000 and now it's down to about 200. and it will continue to shrink until it meets the tolerances that we have specified in the optimization. At the conclusion of the optimization, we'll see how close we are to the data from the characteristics from the data sheet. fmin-con is just one of a number of algorithms in the optimization toolbox, and we selected it because we know that this particular problem is nonlinear, and we wanted to set up a custom objective function. So we can see that fmin-con has completed its optimization. It has brought the two curves as close as possible. At the moment now, we're generating the frequency response curves both with the original values and with the values that fmin-con calculated, and we'll compare those to the characteristics from the data sheet. Okay, so now we have our results. The red line is the frequency response generated by the model with the optimized parameters, and we can see that it is much closer to the characteristics from the data sheet. We could improve this optimization further by including more points, and if we still can't get it close, we could improve our model, adjusting it to include more detail. But we can see that even in this short period of time, with this optimization that we've set up, simply checking 2 points on each curve, we've managed to improve the frequency response much more over the original values that we had. And we were also taking both of the frequency responses into account at the same time. So with this example, we see that with optimization algorithms, we were able to match the characteristics from the datasheet very easily.